morning, all of you. Welcome to Sri Jayendra Hank Zone. So we have successfully completed atomic structure, lecture 1. Now, in lecture 1, we have completed up to electromagnetic radiations. Now, I would like to start this lecture 2 with the same continuation topic of atomic structure. So here in lecture 1, we have completed atomic numbers, mass numbers, electromagnetic radiations, and different atomic models, cathode rays and anode rays. So I want to discuss a few questions based on this because we have not discussed much questions. So now we are adding all these questions to this lecture 1. So this will be seen in lecture 2 also, no problem it is. Now question number 1. One of the fundamental particles is missing in one of the isotopes of hydrogen atom. In one of the isotopes of hydrogen atom, the particle and isotope are respectively. The particles and isotopes are respectively. Here directly write the answer because options we can write, but there's a more time waste. Okay, anyway, I'm discussing the answer directly. So we know hydrogen has 3 isotopes. H has 3 isotopes, 1H1, 1H2, and 1H3. That is 1H1 is protium, 1H2 is deuterium, and 1H3 is tritium. Now in this, if we take the consideration of missing fundamental particles, what are the fundamental particles we have? Electrons, protons, and neutrons. And in 1H1 we have 1 electron, 1 proton, but neutron is missing because 1 minus 1 is equal to 0, because to find mass number 1 minus 1 is equal to 0 means here number of neutrons is equal to 0. So in the first case, neutron is missing, so the fundamental particle is missing. And second case, neutron is equal to 1, electron is equal to 1, proton is equal to 1. So neutron is missing only in the first case, that is 1H1 protium. So the answer is the particle and isotope. The particle is neutron and isotope is protium. So protium. So this is the answer. I hope this you can understand clearly. Next question number 2. The charge of electron an electron is 1.6 in 10 to the power of minus 19 coulombs. What will be the charge on sodium ion? What will be the charge on sodium ion, Na plus ion? So here they are given the charge of electron. Options also I am writing because this question options is important. So option 1, this is previous JEE mains question, 1.6 in 10 to the power of minus 19 coulomb. Option 2, 3.2 in 10 to the power of minus 19 coulomb. Option C, 2.4 in 10 to the power of minus 19 coulomb. And option 4, 10 into 1.6 in 10 to the power of minus 19 coulomb. 10 into 1.6 in 10 to the power of minus 19 coulomb. So for this, usually we'll get understand that sodium ion means atomic number of sodium is 10. So sorry, atomic number of sodium is 11. So it has 11 electrons, 11 protons, but sodium ion is given, so it contains 10 electrons and 11 protons. But here they are asking charge on sodium ions. Charge on sodium ion will be, it is a positive ion, and the nature of positive charge is 1.6 in 10 to the power minus 19 coulombs. So here everyone will get confusion about 1.6 in 10 to the power minus 19 coulombs or 10 into 1.6 in 10 to the power minus 19 coulombs. Because for confusion's sake, they have given the statement the charge of electron is. But here there is no relation with charge of electron. Simply the charge on sodium plus ion. It is a positive ion. So for positive charge, the charge of positive, that is proton, is 1.6 in 10 to the power minus 19 coulombs. So answer is first option. So it is first option. Don't go for fourth option, that is D option, 10 into, because here electrons only for confusion sake he has given, but no need to take into consideration that electrons. So like this questions are expected for JEE mains and NEET, because they want to give one statement based question, and they'll try to shift the students idea mind on that statement so that they can go in wrong answer. So this is the question, that's why I want to discuss this. So I hope this is clear. Next question. The specific charge for positive is, the specific charge for positive is much lesser than, is much lesser than the specific charge for cathode rays, lesser than the specific charge for cathode rays. This is because option 1, positive rays are positively charged. I'm reading the question, you can note down this question in your classwork. Positive rays are positively charged. Positive rays are positively charged. Second point, second option, charge on positive rays is less. Charge on positive rays is less. Third point, positive rays, positive rays comprise ionized atoms, comprised ionized atom whose mass is, whose mass is much higher. And fourth option, experimental method for determination is on. Experimental method for determination is wrong. So this is the question. What is specific charge? Specific charge means E by M ratio. E by M. That is E by M ratio. So E by M ratio for positively charged rays, that is anode rays, is much lesser than that of specific charge for cathode rays, because positive rays or positive charge is not correct. Charge on positive rays is less, and positive rays comprise ionized atoms whose mass is much higher. So this is the answer, because positive rays comprises ionized atoms whose mass each much higher than electrons. So that's why answer is C, because charge of electron is same but mass here, since E by M is proportional to 1 by M, so we can say specific charge for positive rays is lesser than because as the mass of proton is higher than electron, so straight away we can say E prime ratio, that is positive is comprise ionized atoms whose mass is much higher than electrons. So answer is third option. Next question. The conclusions of Rutherford scattering experiment does not include the conclusions of Rutherford scattering experiment. The conclusions of Rutherford scattering experiment. That is alpha scattering experiment. Scattering experiment does not include does not include option 1. So when I'm writing the options, try to analyze the answer. After that only I discuss the answer. So while writing option 1, first A option, alpha particle can come, alpha particle can come within a distance of the order, can come within a distance of the order of the order of 10 to the power of minus 14 meters of the nucleus, of 10 to the power of minus 14 meters, 14 meters. I'm writing it again, 10 to the power of minus 14 meters of the nucleus, of the nucleus. Second point, that is option 2. The radius of the nucleus is less than 10 to the power of minus 14 meters. Radius of nucleus, radius of nucleus is less than 10 to the power of minus 14 meters. Third option, scattering of alpha particles, that is scattering follows Coulomb's law. Scattering follows Coulomb's law. UMB, Coulomb's law. And fourth option, positively charged particles of an atom. Positively charged particles of an atom move with high extreme velocities. Move with high velocities. Move with high velocities. So let us discuss the solution. As you can see all the options clearly. So now here you see alpha particle can come within a distance of the order 10 to the power minus 14 meters of the nucleus. This is correct point. Radius of nucleus is less than minus 14 meters, 10 to the power minus 14 meters. This is also correct. And already you know, as the electrons are revolving around the nucleus, because nucleus is positively charged from Rutherford's model, scattering follows Coulomb's law, that is Coulomb's law of electrostatic force of attraction. This also we discussed in the options. And fourth one, positively charged particles of an atom move with high velocity, that he could not explain. So that is not, this is not included. So answer is fourth option. So this is not included in the Rutherford's model. I hope this is clear for you. Next question. The ratio between next question. The ratio between the neutrons between the neutrons present in carbon atom and silicon atom with mass numbers 12 and 28 is with mass numbers 12 and 28 is. So here I am not giving options, straight away we will find out the answer 12 and 28. So they are given carbon 12 and silicon is 28. So already we know solution. I'm starting now. So we have to find number of newtons ratio. So first we'll find the number of newtons in carbon atom as well as silicon atom. So carbon 12 means carbon atomic number is 6 and it is 12 given. Carbon 6 12 and silicon 14 and 28. 14 and 28 because the atomic number of silicon is 14. So number of newtons in carbon, N in carbon is equal to N in carbon is equal to, just if you find the number of newtons, N in carbon is equal to, that is number of newtons in carbon is equal to 12 minus 6, that is A minus Z equal to 6. Similarly, number of newtons in silicon is equal to, number of newtons in silicon is equal to 28 minus 14, which is equal to 14. So the final ratio is 6 is to 14, that we can still further write it as 3 is to 7. And the ratio between newtons present in carbon atom and the silicon atom is 3 is to 7. So like this also, the questions will come. So it's very important for the discussion. That's why I have kept it here. Next question. Next question. The radiation having maximum wavelength is. So this question is based on electromagnetic radiation. The radiation having maximum wavelength is. So we have given the, in the previous lecture, we have given the electromagnetic radiation, the chart, which is having maximum wavelength, which is having minimum wavelength, and X-rays, gamma rays, etc., etc. So radio waves, all the wavelengths and frequencies are given. The radiation having maximum wavelength is, first option UV rays, second option radio waves, third option X-rays, and fourth option infrared rays. So if you can recollect the diagram, so in the diagram you can clearly see from left to right the increasing wavelength, and from the top, that is left to right increasing wavelength, and right to left increasing frequency, because frequency and the wavelength are inversely proportional to each other. Higher wavelength, less frequency, less wavelength, higher frequency. So in that case, if you see, X-rays and gamma rays are having highest frequency because they are in the range of 10 to the power 24 hertz, whereas radio waves, in these given options, radio waves are having maximum wavelength because that it is in the right hand side of the diagram. So radio waves is the answer. So you can see this answer in the diagram. So radio waves, you can recollect the diagram having, so radio waves is having maximum wavelength. So this type of questions also you may expect for the competitive exams. Next, the product of the following, last question in this for the class 1 lecture, which I want to add. Next we'll continue with the PPTs. The product of which of the following is equal to the velocity of light? The product of which of the following is equal to velocity of light? So direct answer, velocity of light. So from wave theory of light, we know nu is equal to c lambda. Nu is equal to c by lambda. Solution direct, I'm writing, I'm not giving options. Nu is equal to c by lambda. Implies lambda is equal to, they are asking velocity of light. C is equal to nu lambda. C is equal to, because C is velocity of light, C is equal to nu into lambda. So the product of which means here frequency into wavelength. So frequency into wavelength is the answer. So I hope you can understand. Next, We'll continue with the lecture 2, the same after electromagnetic radiations. What is the next topic? That is the particle nature of light. Very, very important. So till here we have completed up to electromagnetic radiations. You can verify NCERT textbook also, and even objective point of view. Next we are going to do particle nature of light. Light is associated with particle nature, which can be illustrated by the following properties. That is, first one is black body radiation, second one photoelectric effect, and third one variation of heat capacity of solids with the temperature, and fourth one spectra of atoms. So in this hour we are going to discuss about all these things. So light is a form of energy, and light is associated with the particle nature as well as it has wave nature also. That is why we will say discuss dual nature of light. But now here we are discussing light as particle nature, and based on the particle nature of light we have black body radiation, photoelectric effect, and variation of heat capacity of solids with temperature, spectra of atoms. Now continuation. What is black body radiations? A body which can observe or emit radiations of all frequencies. It can observe and emit radiations of all frequencies is known as black body, and the radiation emitted by such bodies is known as black body radiation. Black body radiation. Now the frequency distribution of emitted radiation of a black body depends only on its temperature. The intensity of the emitted radiation varies with wavelength. As the wavelength decreases, the intensity increases, reaches a maximum, and again decreases. So I hope this easily you can understand. The frequency distribution of emitted radiation of black body depends on its temperature. Very, very important point. The frequency depending on the temperature. The intensity of the emitted radiation varies with wavelength. As the wavelength decreases, the intensity increases, reaches a maximum, and again decreases. So let us see. So a black body is nothing but it emit and absorb all the radiations of all the frequencies. That is, all the frequencies in the sense gamma is to even you can say radio waves and so on. So all the frequencies, and it can emit and absorb all the radiations of frequencies is called a black body. Now continuation of black body radiation. You can see the graph. So intensity and wavelength. Here the intensity and wavelength. Intensity decreases with the increase of wavelength. With the increase of wavelength, the intensity decreases, and with respect to temperature, the black body radiation depending upon temperature. So classical theory at 5000 kelvins it reaches maximum, and afterwards it starts decreasing. So as the increase in wavelength takes place, the radiation decreases. So this is called a black body radiation diagram. Based on this diagram also they can ask questions. So here intensity and the intensity of light is given on the x-axis, and wavelength is given on the intensity of light on the y-axis, and wavelength is given on the x-axis. So here you can see with zero wavelength, high temperature, black body radiation is higher, and as the wavelength increases, the frequency decreases automatically. We know intensity also decreases because intensity is proportional to frequency. Next, Planck's quantum theory. This is very, very important theory. So based on Planck's quantum theory, all the bodies emit only discrete packets of energy called quantum. Each quantum is associated with an energy which is proportional to its frequency. And from Planck's quantum theory, we got from Einstein's equation, we know E is equal to mc square. And from Planck's quantum theory, we got E is equal to h nu, where h is called Planck's constant and nu is called frequency. The emission, let's see here, Planck's quantum theory. All the bodies emit or absorb radiations only in discrete packets of energy called quantum. Each quantum is associated with an energy. So E is equal to h nu, and energy is proportional to frequency. And for removing proportionality, we have to use constant, and this constant is called Planck's constant, where h is equal to Planck's constant. Its value is 6.625 in 10 to the power of minus 35 joules second. Joule second, h is joule second. So unit of h is joule second. Joules per second, no, joule second only. So this is called Planck's quantum theory. So energy, all bodies emit or absorb radiations only in discrete packets called quantum. And each, according to Planck's quantum theory, each quantum is associated with an energy which is proportional to frequency. Simple. So energy is proportional to frequency. Now, the emission or absorption of radiation takes place only in integral multiples of quantum. That is, E is equal to nh nu or nhc by lambda, where n is equal to 1, 2, 3. So this is called Planck's quantum theory. And from the Planck's quantum theory, the possibility formula is, you can see here one question I'll just discuss. Simple question I want to discuss from Planck's quantum theory. There itself I'm discussing now. Here itself you can write. Yes, just I want to discuss the question based on Planck's quantum theory. Just note down. Simple question. This is so many times this question has come for a competitive exam. So the ratio of energies of photons. The ratio of energies of photons with wavelength 2000 angstroms. Energies of photons with wavelength 2000 angstroms and 4000 angstroms is 2000 angstroms and 4000 angstroms is. So we know that from Planck's quantum theory, solution I'm writing here, E1 is equal to hc by lambda 1 and E2 is equal to hc by lambda 2. By this you can write E1 by E2 is equal to lambda 2 by lambda 1. E1 by E2 is equal to lambda 2 by lambda 1. Since h and c are constant, we can write E1 by E2 is equal to lambda 2 by lambda 1. Straight away we can write. So by substituting these values, lambda 2 is given as 4000. So 4000 by 2000. That is equal to 4000 by 2000. That is in the form of 2:1. So answer is 2 by 1, which is equal to E1 by E2 is equal to 2:1. So answer is 2:1. In this way, they'll ask the questions from Planck's quantum theory. I hope this is clear for you. Next, we'll go in detail about Planck's quantum theory. So the is Planck's quantum theory. Next, we'll discuss continuation topic. Planck's quantum theory E is equal to nhc by lambda. Next, we have E is equal to h lambda h nu, where nu is equal to c by lambda from wave theory of light. Next, we'll continuation example 1. Calculate the energy of photon having wave number 3 into 10 to the power 7 meter inverse. So this is again second question Planck's quantum theory. So I'm writing here the solution. Before going to solution, once we discuss, we have to find energy of photon. They are asking to find energy of photon. We know from Planck's quantum theory, E is equal to h nu. E is equal to h nu, where nu is called frequency, or you can write E is equal to h into c by lambda. E is equal to h into c by lambda, because nu is equal to c by lambda, and they have given wave number. So already we know 1 by lambda is equal to wave number. 1 by lambda is equal to nu bar, that is wave number 1 by lambda. So they have given wave number 3 in 10 to the power 7. So we can write E is equal to energy is equal to h into 1 by lambda, or you can write E is equal to h into wave number. E is equal to h into wave number. E is equal to h into wave number, because 1 by lambda is 1 by lambda is h into c into wave number. So h into c into wave number, h into c into wave number. E is equal to h into c into wave number, because 1 by lambda is equal to wave number. We can write E is equal to h into c into wave number. So straight away applying this formula, we can get the answer. So E is equal to h value is 6.625. So continue with the solution. E is equal to that is equal to h value, 6.625 and 10 to the power of 34 minus 34 or 34 minus 34 into c lambda is 3 in 10 to the power of 8 meters per second, and into 3 into 10 to the power of 7. So by solving this, we'll get the answer. So I hope this question you understood clearly. So answer is, here I'm writing the answer. The answer you can check. It is equal to 5.96 in 10 to the power minus 18 joules. So you have to apply the formula E is equal to Hc nu bar. E is equal to Hc into nu bar. Just applying this formula, you get the answer. Nu bar is given, that is wave number 3 in 10 to the power 7. Planck's constant value you know, and C value is 3 in 10 to the power 8 meters per second. I hope this is clear. Next example 2, based on Planck's constant. The frequency of yellow line in the spectrum of sodium is 5.09 10 to the power 14 second inverse. They are given the frequency. You need to find energy of photon of this radiation. So straight question, E is equal to h nu. The formula is what? E is equal to h nu, because from photoelectric, this from Planck's quantum theory, we got E is equal to h nu. H value is Planck's constant, we know, and nu value they are given directly 5.09 say 10 to the power 14 second inverse, and they are asking us to find energy of photon. So energy is equal to h nu. So by applying this formula, you get the answer, and the answer for this you can check it out. So I am giving directly answer. You can do calculation part. E is equal to 3.372 10 to the power minus 19 joules. Next, example 3. Calculate the number of photons having lambda is equal to 100 nanometer, which can provide 1 joule of energy. This is very, very important model. Just making it important model. You can just see here in the Planck's quantum theory, we got the last formula, number of photons. They have given number of photons. So simple, the formula is simple. So E is equal to NHC by lambda. E is equal to NHC by lambda with respect to number of photons, where N is called number of photons. So from this formula, now they have given in this question lambda also, they have given lambda, they have given energy also, that is equal to 1 joule, and they are asking us to find n value, that is number of photons. So in this case we have to find n value, because h value is Planck's constant, c value is velocity of light. So c is equal to 10 to the power 8 meters per second. So h value is also we know Planck's constant value. So remaining also, by this you can write n is equal to E lambda by hc. E lambda by hc, that is 1 into so you substitute this formula straight away and take the values. E value is given, and the lambda value is given. H value you know, C value you know. By substituting all this, you'll get the answer. And the answer for this question is, just work out clearly as I open up the solution. So answer for this is 5.03 10 to the power 17 photons. So we have for this question 5.03 10 to the power 17 photons. This, so from Planck's quantum theory, we have 4 different models we have done. First model is E1 by E2 is equal to lambda 2 by lambda 1. That is comparison of energies with respect to wavelength. Even with respect to frequencies also we can do. E1 by E2 is equal to nu 1 by nu 2, because frequency is directly proportional. So second case we have done E is equal to hc by lambda, and from that we can find new wave number, that is E is equal to hc nu bar, that is nu bar is nothing but wave number. And third one we have find different case, that is E is equal to number of photons. How to calculate number of photons, we can do like this. So I hope this is clear for you and very, very important. Next we have, based on black body radiations, after the Planck's quantum theory, we have next concept, photoelectric effect. It is very, very important topic. So photoelectric effect is much more important. And when a beam of radiation of certain frequency is made to fall, when a beam of radiation of certain frequency is made to fall on the surface of a particular metal, electrons are ejected out of the metal surface. This phenomenon is called ejection of electrons from the surface of the metal by the incident radiation is known as photoelectric effect. So simple it is. Take a metallic surface, and on that metallic surface, if a light of certain frequency is incident, when a beam of radiation of certain frequency is incident on the metallic surface, since you know metallic surface contains free electrons, because all the metals are good conductors of electricity. So the metallic surface contains free electrons, and after a certain time of interval, you'll notice that the ejection of electrons takes place from the surface of metal, and this ejection of electrons from the surface of metal by incident radiation is commonly called as photoelectric effect. But in these, two things are happening here. So first, light of certain frequency is incident on the metallic surface, and the metallic surface gets activated, and due to this what happens, light is a form of energy. It gains a the metallic surface gains energy, and due to which what happens, as the metal contains free electrons, so these electrons will absorb, the energy of the light is absorbed by electrons, and hence they started vibrating from the mean position and try to come out. That is called ejection of electrons. This is commonly called as photoelectric effect. So very, very important. In this, definition is simple, but understanding the numerical part is very, very difficult. Please try to understand properly. It's very, very important concept. Next, characteristics of photoelectric effect. There is no time lag between striking of light and ejection of electrons. After some time means it's fraction of seconds. So that's why we can say there is no time lag between striking of light and ejection of electrons. The photoelectric emission is absorbed only above a characteristic minimum frequency known as threshold frequency. This point is important. That threshold frequency. What is threshold frequency? The minimum frequency attained by the metallic surface, electrons, metallic surface. So the photoelectric emission is observed only above a characteristic minimum frequency known as threshold frequency. So this threshold frequency should be, this threshold frequency is most important. The frequency of the radiation is above the threshold frequency. The excess energy is converted to kinetic energy of photoelectrons. So if the frequency of the radiation is above the threshold frequency, the excess of energy is converted to kinetic energy. Suppose if the radiation of light is less than threshold frequency, actually what is threshold frequency? The frequency of the metallic surface of the electrons frequency of the metallic surface, which is residing on the metallic surface. Once the metal surface reaches threshold frequency, then only they start emitting out, ejecting out electrons. Otherwise, there is no ejection of electrons. That's why the main condition is that is frequency of radiation nu. That is frequency is nu. So I'm writing here nu is called frequency of light. Nu should be greater than nu naught, where nu naught is called frequency of threshold frequency. So threshold frequency is nu naught. That is the frequency which is attained by the electrons of metallic surface. And if the frequency of light is less than nu naught, then there is no ejection of electrons. That is most important. So the important condition for photoelectric effect is nu should be greater than nu naught. This is most important condition. If the frequency of the radiation is above the threshold frequency, then only excess of energy is converted into kinetic energy of photoelectrons, from where we'll get ejection of electrons. As the electrons are moving, any moving particle will have kinetic energy. So we have to consider two things very, very important. That is, first case, work function of the metal. That is, the light it is observing, the metallic surface is observing the light, which is a form of energy, and doing work, that is ejection of electrons, that is called work function of metal. And the second one is kinetic energy. So these together, these two things will form photoelectric effect. From there only we can derive the formula. What is photoelectric effect formula? So let us see now. Here I'm clearing the, moving to the next slide. The kinetic energy of the photoelectrons is proportional to the difference in the frequency of radiation and the threshold frequency. And the number of photoelectrons emitted is directly proportional to the intensity of radiation. So coming to this point, the kinetic energy of the photoelectrons, K is proportional to the difference in the frequency of radiation and the threshold frequency, because this also will derive the formula, then only can understand easily. The number of photoelectrons emitted is directly proportional to the intensity of radiation. Now, this is the characteristics of photoelectric effect. The important condition is the frequency of light, nu, should be greater than threshold frequency. That is the frequency of the metallic surface, electrons of the metallic surface. That is commonly called as threshold frequency. Now, coming to this, we have metallic function, work function of metal. As I told you, it has two important things taking place in photoelectric effect. The minimum energy required to cause photoelectric effect from a metallic surface is known as work function of the metal. It is expressed in electron volts per atom. And if nu naught is a threshold frequency, then the work function is given by E is equal to H nu naught. H nu naught. Work is also a form of energy. So E is equal to H nu naught, because E is equal to H nu is there from Planck's quantum theory. So E is equal to H nu naught. This is called work function of metal. So you should note down what is work function of metal. That is E is equal to H nu naught. Next, if nu naught is the threshold frequency and nu is the frequency of incident radiation, and the condition should be very, very important, that nu should be greater than nu naught, then only kinetic energy of the photoelectrons is given by h nu minus h nu naught. That is difference in the photoelectric effect. That is in energy of light of radiation minus energy of work function of the metal is equal to half mv square. That is kinetic energy, where m is called mass of electron, v is called velocity of photoelectrons. So these are the formulas from photoelectric effect. We have main formula from photoelectric effect is kinetic energy Ke is equal to h nu minus h nu naught. Kinetic energy Ke is equal to h nu minus h nu naught. Ke is equal to h nu minus h nu naught, where h nu is called energy of the frequency of radiation and h nu naught is called work function of the metal. Work function of metal is called h nu naught. Work function of the metal is equal to h nu naught. So these two formulas you have to remember, so that, and where nu naught is called frequency. From this we can also add kinetic energy is equal to kinetic energy. Here itself I am writing kinetic energy is equal to, since h nu is equal to h into c by lambda, we can add h into c by lambda minus h into c by lambda naught, and h into c common, taking common, we can write kinetic energy is equal to kinetic energy is equal to kinetic energy is equal to h into c into 1 by lambda minus 1 by lambda naught. So in this case, if they are given wavelength of the light as well as threshold wavelength of the light, and metallic surface, if they are given threshold wavelength and wavelength of light, we have to use this formula. So these are the four formulas which we are going to apply in photoelectric effect. Very simple. Next, I hope this is clear for you. Photoelectric effect and problems based on photoelectric effect is most important for the exams. So when electromagnetic radiation of wavelength 200 nanometers falls on surface of metal, so they are given wavelength of light, that is 200 nanometers, falls on surface of metal. Electrons are emitted with a kinetic energy of 2.5 10 to the power 5 joules per mole. What is the work function of the metal? So they're asking what is the work function of the metal and what is the maximum wavelength which can cause photo emission of this metal. So coming to work function of the metal, we can say straight away kinetic energy is equal to, solution I'm writing here, just see there, I'm giving the idea, then we can substitute. So we know kinetic energy is equal to h into c into kinetic energy is equal to h nu minus h nu naught, and h nu naught is called work function. H nu naught can be taken as h into c by lambda minus h into c by lambda naught. Since they are given wavelength hc into h into c by lambda, h into c by lambda, h into c by lambda minus h into c by lambda naught, and they are asking work function of the metal. So this is called work function of the metal. H into c by lambda naught is called W, and sending W to that side, kinetic energy this side. So W is equal to that is work function of the metal, Hc lambda naught, Hc by lambda. W is equal to kinetic energy plus kinetic energy minus kinetic energy. So h into c by lambda. First we have to find out h into c by lambda. So they are given h value, that is h value is Planck's constant, kinetic energy is given, and the lambda is given 200 nanometers. C value, 3 into 10 to the power of 8 meters per second. And this 200 nanometers you have to convert into meters, that is 10 to the power of minus 9. So the final expression becomes work function W is equal to work function W is equal to H, that is Planck's constant, 6.625 10 to the power minus 34, 6.625 10 to the power minus 34, between 10 to the power 8 meters per second, that is C value, and lambda divided by lambda divided by 200 into 10 to the power minus 9, and plus minus kinetic energy. Kinetic energy should be written at the top, so we cannot write it over there. Minus 2.5 10 to the power of minus 10 to the power 5 joules per mole. By substituting these values, you'll get the answer directly. So I hope it is clear. I'm directly giving the answer, that is 344 nanometers. 344 nanometers. Next example. The threshold frequency of metal is 7 in 10 to the power 14 second inverse. Calculate the kinetic energy of electron. They are asking here us to find kinetic energy. So threshold frequency nu naught is given. Kinetic energy we have to find when the radiation of frequency of the light is also given 1 into 10 to the power 1.8 10 to the power 15 second inverse. So strikes the metallic surface. So kinetic energy is equal to how much? Kinetic energy is equal to h nu minus h nu naught. That is h into nu minus nu naught. You can take h into nu minus nu naught. Nu is called frequency of light and nu naught is called 1.8 10 to the power 15 minus 7 10 to the power 14. So for this we have to calculate. Just I'm showing the calculation also. Take it as 1.8 in 10 to the power 15 can be taken as 18 10 to the power 14. 18 into 10 to the power 14. So that we can write, you can easily subtract because 10's power should be equal 18. 18 into 10 to the power 14 minus 7 into 10 to the power 14. So which is commonly 8 minus 7 is equal to how much? 11 into 10 to the power 14. So h into 10 to the power 14, 11 into 10 to the power 14 is the answer. So h value is 6.62 10 to the power minus 34. So by substituting all these things, you'll get the answer. So I hope this you can understand clearly. So answer is 7.287 10 to the power minus 19 joules. So this is called example 5, threshold frequency. So very, very important. I hope. Next question. Electrons are emitted with zero velocity from a metallic surface when it is exposed to radiation of wavelength 5700 angstroms. 5700 angstroms they are given. Calculate the threshold frequency and work function of the metal. So first they are given the wavelength of the light. From the wavelength of the light we can find frequency of the light and then threshold frequency as well as work function. So work function. And electrons are emitted with zero velocity from metallic surface when it is exposed to radiation of wavelength. So from wavelength we can find frequency. So nu is equal to c by lambda. Nu is equal to c by lambda, and that is equal to 3 in 10 to the power of 8. Sorry, 3 in 10 to the power of 10 we have to take here because they are given angstroms by 5700 10 to the power of minus 8. Angstroms is 1 angstrom is 10 to the power of minus 8 centimeter. So 5700 10 to the power of minus 8. By substituting this, you will get the value of frequency. After getting the value of frequency, you can find threshold frequency and work function of the metal. And they have given zero velocity. So kinetic energy becomes zero. Very, very important. Zero velocity means kinetic energy becomes zero. So kinetic energy zero is equal to h nu minus h nu naught. Zero is equal to h nu minus h nu naught. So from this we can find out h nu already we know how to find. So by this we can write h nu is equal to h nu naught. So whatever the value of h nu we are finding, that is only nu is equal to nu naught. So in this way you can find out work function of the metal also. Work function of the metal, because no ejection of electrons takes place. So we can find work function of metal using nu is equal to nu naught. So h into nu is nothing but work function of the metal. Next answer I'm giving here, just see it. So 2.717 electron volts. This electron volts, you have to convert the joules into electron volts. That is also we have to do it. Next. So next topic, based on photoelectric effect, we have done 3 to 4 examples. Next we have, what is spectrum? It is a regular pattern of lines or bands obtained in a photographic plate due to interaction of matter with electromagnetic radiation. The spectrum obtained is characteristic substance used of the spectrum obtained is the characteristic of the substance used, and useful information can be obtained in the spectrum. So a spectrum is nothing but a pattern of lines or bands obtained on a photographic plate due to interaction of matter with electromagnetic radiation. So already we know atomic spectrum or hydrogen spectrum, etc. Like that we have spectrum. When a white light is incident on a prism, it gets diffused into 7 colors by giving Ujja. That is the only spectrum you know in physics experiment. So here atomic spectrum we are going to learn in this topic. So what is spectrum? Basically, it is a regular pattern of lines or bands obtained on a photographic plate due to interaction of matter with electromagnetic radiation. The spectrum is obtained is characteristic of the substance used, and useful information can be obtained from the spectrum. So all the spectrums are not same. So it depends upon substance. Next types of spectra. There are only two types of spectra. One is emission spectra, and there is absorption spectra. So what is emission spectrum? Atoms, ions, or molecules absorb energy and reach the higher energy state or auxiliary states where they are unstable. These atoms or ions molecules come back to normal state by emitting absorbed radiation, which will appear as a spectrum known as emission spectrum. Means here, for atoms, ions, or molecules, they absorb energy and reach the higher state. Means the atoms or the electrons or the ions or the molecules. These are the small substances, very, very small, which already we know. So when they absorb energy, that is light, light is a form of energy since you already know. They reach the higher energy state or auxiliary states where they are unstable. And these atoms or ions or molecules come back to normal state by emitting the absorbed radiation. So by emitting the absorbed radiation, they will come back to normal position, which will appear as a spectrum known as emission spectrum. The emission spectrum will contain bright lines separated by dark spaces. So when radiations are passed through a sample of substance, certain wavelengths will be absorbed by the substance. The missing wavelength or frequencies will appear as dark lines in a continuous bright spectrum. So this is called absorption spectrum. Absorption here, and there it is emission. When the radiations are passed through a sample of substance, certain wavelengths will be absorbed by the substance. The missing wavelengths or frequencies will appear as dark lines in a continuous or band spectrum. So spectrum, continuous spectrum, discontinuous. In this continuous spectrum, discontinuous. In discontinuous, we have two types. One more line is line spectrum and band spectrum. What is line spectrum? A discontinuous spectrum means it will be continuous, consisting of distinct and well-defined lines. Very small lines separated by dark spaces is called line spectrum. Emission spectrum of gaseous atoms will be line spectrum. Example, hydrogen spectrum. Hydrogen spectrum is an example of line spectrum. So this is called line spectrum. Next we have band spectrum. The emission spectrum obtained by molecules will have bright bands separated by dark spaces. It is also known as molecular spectrum. So band spectrum, it is also continuous spectrum. So what is spectroscopy? The study of spectrum of elements or molecules or atoms or ions is known as spectroscopy. By the means of spectrometer, we can study all these things. Spectroscopy can be used in chemical analysis to identify an unknown atom or molecule. Elements like rubidium, cesium, thallium, indium, gallium, and scandium were discovered when their compounds were studied by spectrographic methods. So it is very, very useful spectroscopy. Next, coming to hydrogen spectrum. So since already we know hydrogen spectrum is in a band spectrum, so a line spectrum. So when the energy is incident on hydrogen atom, what happens? The electron, we know already hydrogen has only one electron. This one electron absorbs that energy and it goes to higher excited state. That is, and while after reaching higher excited state, as it is unstable over there, the electron may tends to fall down again from higher state to lower state. And in this journey, it forms a series of lines. And what are those series of lines? We have Lyman series, where N2 value is greater than 1, means higher energy level is greater than, it can be infinity, it can be 7, 6, 4, 5, 3, and so on. And N1 is equal to 1. So that is first orbit. And the series belongs to ultraviolet region. This table is very, very important for all the series. So hydrogen can form, these are the following series: Lyman series, Palmer series, Pastian series, Brackett series, P fund series. So if N1 value is equal to 1, so if the electron jumps from any of the higher energy orbit is equal to n is equal to 1, means if the electron jumps from any of the higher energy orbit, that is infinity to 1 or 6 to 1, 5 to 1, 4 to 1, then a series of lines are formed, which are commonly called as Lyman series. This series, Lyman series examples, we'll discuss more in post theory, but here it's very important for discussion of spectrum, so that's why we have kept it here. And the Balmer series, when the energy of the electron means the electron is jumping from any of the high energy orbit, that is infinity, 7, 5, 4, 3, and up to 2, means it is the lowest state is 2 only, it is not going to 1. So that is called visible region, which is also called as Balmer series. Balmer series is found in visible region. Passing series near infrared region, and bracket says infrared region, and fund says far infrared region. So this is called hydrogen spectrum. N2 has only integer values, that is infinity to infinity 7, 6, 4, 5, and so on. So this is called hydrogen spectrum. And expression of wave number of lines in hydrogen spectrum, very very important. This is called as Rydberg's equation. From spectrum only we got Rydberg's equation. The wave number of spectral lines is calculated using Rydberg equation. So wave number is already, this is denoted by letter nu bar. It is denoted by the letter nu bar. Nu bar is equal to 1 by lambda, which is equal to r into 1 by n1 square minus 1 by n2 square. This formula is most important, and problems based on this formula is very important for all competitive exams, whether you are at JEE mains or NEET or IIT advanced anything. This formula is most important. So please note down this formula. Wave number is equal to 1 by lambda, which is equal to r into 1 by n1 square minus 1 by n2 square. This formula is very important. Kindly note down. So for Lyman says n1 is equal to 1, already we know. N2 can be 2, 3, 4, 5, means greater than 1, and it can be up to infinity. Similarly for Balmer says n1 is equal to 2 and n2 is equal to 3, 4, 5, 6. So this table is very important, because they'll ask the question like this: find the wavelength of electron in Balmer series, or find the wavelength of electron in Balmer series when the electron jumps from second orbit to third orbit, like that. Even they'll say Balmer series, or they'll say any orbit number also. If they are given orbit number, it's easy. But if they are given only Balmer series, Lyman series, you need to know the limits. For Balmer series, the limit is n1 is equal to 2, n2 can be 3, 4, 5, 6, because they give only one orbit number. Similarly, n1 is equal to 3, n2 is equal to 4, 5, 6, 7 for Partian. N1 is equal to 4 for bracket series, N1 is equal to 5 for fund series. So for Lyman series, when the electron is jumping from any of the higher energy orbit, but lower energy orbit, N1 is equal to 1. I hope this is clear for you. So this table is very important, and this formula is very important. And how we will get questions based on this formula, we are going to discuss later. Now, next we have what is the limiting line of spectral series. In any spectral series, the last spectral line is known as limiting line of the spectral series. This line will be the spectral line with highest frequency and lowest wavelength. So underline this: highest frequency. Every limiting line will have highest frequency and lowest wavelength. Highest frequency and lowest wavelength. To calculate wave number or wavelength of the limiting line, N2 is taken as infinity. Here N2 is taken as infinity is most important. So for example, you want to find the limiting line of, just writing here, I'm giving example. Find the wavelength of limiting line of Lyman series. So for this case, 1 by lambda is equal to, we are calculating limiting line of Lyman series for wavelength. So 1 by lambda is equal to R into, that is RH is Rydberg's constant, R into 1 by bracket 1 by n1 square, that is 1 square, minus 1 by n2 square, and n2 should be taken as infinity here. So n1 square is 1 and n2 square is infinity. So r into 1 by 1 minus 1 by infinity square. So for limiting line of Lyman series is r, which is equal to r. Similar limiting line of Balmer series becomes 1 by 1, n1 square becomes 2 square, that is 4. So r by 4. Like that we can find out limiting line for all the series of hydrogen spectrum. So what is limiting line? In any spectral line series, the last spectral line is known as limiting line of the series. This line will be the spectral line with highest frequency and lowest wavelength. To calculate the wave number or wavelength of the limiting line, N2 is taken as infinity in the Rydberg's equation. So already for Lyman series, N1 is equal to 1. For Balmer series, N1 is equal to 2, and so on. So I'm ending this session. So next session we'll do more about hydrogen spectrum and all. Thank you.